Yeah, I'm glad to be able to talk to you today. So I'm going to talk actually about a problem that's quite similar to the problem described in the last talk, but at a very different scale. So the first thing that I want to say, and I think that this is a point to base it, that most people who work in molecular simulation will understand intuitively, is that for most complicated biomolecular systems at a scale that's larger than the size of an individual protein will require some amount of coarse graining to be able to tractably simulate on timescales that are relevant for biological organization and for all of the processes that these things carry out. This is a pretty fundamental limitation. I don't really think that this is something that is solved by better computers or better multiple time stepping algorithms. I think that those things can help understand behaviors on short time scales, but we're talking about things that span time scales from seconds to minutes to hours, which, because of the constraints on the stiffness of our numerical integrators for molecular simulators, are not going to be able to ever be overcome. So this is a pretty fundamental thing. And when we look at, something as complicated as, this is an example from my own research, but, it applies to many other things. The carboxysome, this is a biological system that self-organizes over a very large time scale. It self-assembles in cyanobacteria. So this is a system that's important for carbon fixation. It's in cyanobacteria that live on the surface of the ocean, and they contain a mixture of enzymes, carbonic anhydrase and rubisco, and it fixes carbon. Sort of like a little nanoreactor in some sense. And when you study a system like this, explicitly representing all of the molecular degrees of freedom is likely unnecessary for many questions that you might ask about it, say, is like, what is the interplay between the elastic properties of this protein shell with the assembly of the cargo? And those sorts of questions invite a sort of traditional approach to coarse graining, in which one would look at a system like this and say, okay, what are the salient physical features that I would like to represent? And then you build a model around that, right? So we, in a sort of ad hoc way, or a physically inspired way, we, choose a representation of this where we say, okay, well, we don't actually care about, representing the carbonic anhydrase explicitly. So we're just going to represent it as a condensed cargo that, has some propensity to agglomerate. And we don't really care about representing, these protein shell proteins explicitly, but we do care about their energetic, elastic properties. So we're going to represent it as like a Helfrich style Hamiltonian, where, there's some amount of bending rigidity. There's an intrinsic stiffness to all of these components. And that will actually provide, in some sense, a salient representation of the underlying system with which we can study its thermodynamic properties, its assembly dynamics under different characteristics. And that ends up being a sort of useful paradigm in many cases. However, coarse graining biomolecular systems is a very challenging prospect for a number of reasons. So, we can design around a particular physical problem and try to build a particular minimal model. But there are many systems, and I think lipid bilayers are perhaps the most indicative of these sorts of problems, for which we don't really know what the salient physical features are that will actually drive the dynamical and thermodynamic behavior that we're interested in much of the time. So, one famous model of a coarse-grained, or one famous coarse-grained model is the Martini model, which is a very popular representation of lipids that's used kind of ubiquitously. And it sort of raises the first question in actually building a coarse-grained representation, which is, if I were to build a coarse-grained representation, I have to make some choice as to which degrees of freedom I project out. And typically that choice of which degrees of freedom I project is independent of, the state of the system at a given point in time, right? So you could imagine that it might be advantageous to project down, different clumps of atoms at different points in state space, but typically this is not done. And instead what is done is a projection matrix is fixed, and that choice is a completely user-defined choice, right? It's a choice that I make at the beginning, and I say, okay, these are the atoms that I'm going to retain, or I'm going to group these clusters into specific degrees of freedom that are going to evolve, together. And just to kind of point this out, the typical approach is to use linear projections. So we group together atoms and we project out quite a lot of information. And then, we build a representation of the underlying potential for this. That potential is something that has started to be explored with machine learning, right? It's something that people have started to parameterize partially with machine learned potentials. And that is actually shown to be quite important to retaining some of the higher order correlations that are lost when you reduce the dimensionality. So the second kind of complication of coarse graining in this way is that you're left at the end with a coarse-grained model, and that model is contains exactly as much information as you allow, right? So you have made the choice to reduce the dimensionality, and the only thing that remains from the system that you end up obtaining statistics from are the degrees of freedom that you have retained. So the interpretation of what the system means in a given configuration becomes complicated. We don't have access to the fine-grained state anymore, and we sort of think of the representation that we obtain as being representative of a particular fine-grained state, but really it's a conditioned ensemble of fine-grained states that correspond to one projection of the system. And actually obtaining that ensemble and assessing molecular properties of the resulting structures is not trivial by any means, especially when the empirical potential that we learned for the system, right? So once we've reduced the dimensionality, we have to build a new potential energy function that describes the statistics of the system through the Boltzmann weight of that learned potential. So typically that's used to recapitulate the potential of mean force on the coarse-grained degrees of freedom. However, we don't learn that perfectly, right? I mean, it's a statistical problem to obtain that, and it is one that requires typically large amounts of data. And if we use a model that's not sufficiently flexible, like the sort of traditional empirical potentials that are used for coarse-grained modeling, there's an inherent bias in the representation. So those are both interpretation of thermodynamic states, thermodynamic quantities, but there's also a challenge in interpreting the dynamics. So rigorously there is a kind of defined formalism for obtaining dynamical information from a coarse-grained model. It's the Mori-Zwanzig formalism, but it's pretty impractical. It's very, very difficult to actually use this. So I mean, there's there are interesting efforts to try to use it, but I don't really know. I mean, this is something that I'd be open to hear from any of you who have knowledge of this more about, because as far as I'm aware, there's no sort of well accepted framework for doing this in a practical system. And then finally, the real challenge in building coarse-grained models is often computation. So the quality of generalization within a model is kind of the key benchmark for whether or not coarse-graining is productive. So many coarse-grained models are built with quantities of data that are sufficient to answer the questions that we might set out to answer with the coarse-grained model. So you really need to achieve, this level of independence for the coarse-grained model that allows you to explore new regimes of the thermodynamic state space that haven't really been explicitly contained within the data. And of course, as I think as was brought up in the discussion for the last talk, this requires that you have relevant rare configurations for things like transition states or other types of dynamical events that are that are crucial in order to actually, represent those regions of the thermodynamic state space. And within this kind of traditional paradigm of, project, then learn a potential, and then run dynamics, that also means that there are limited opportunities for feedback. You cannot take a coarse-grained configuration or an ensemble of coarse-grained configurations and use them as further data for training a model, right? So there's no ability to kind of close the loop of, augmenting your data set with data collected from the coarse-grained model. So, in the spirit of of thinking about where machine learning can actually enhance some of the things that we use in molecular simulation, we're going to kind of take an approach where we learn most of these things. And so we first, need to ask this question, why is machine learning useful in this setting? So there's a plot that I like to include in talks. I think if any of you have seen me give a talk recently, you'll have seen this plot, which is actually from a blog post by OpenAI. And the plot is rather complicated and the text is small, so it might be hard to read. But essentially what this shows is, as a function of time, so in years, right, from 1960 to now, how has the computational effort required to train state-of-the-art models grown? So until about 2010, the computational effort required to train, these various state-of-the-art models, so everything from a perceptron in 1960 to, deep belief networks in about 2007 or 2006. The cost to train these models grew roughly at the rate of Moore's law. So that's to be expected, right? So the cost of training is kind of growing in proportion to our computational power. So, that's something so we're still growing at Moore's law rate in terms of computational power. But if you look around 2012, the rate of doubling in computational effort for machine learning started vastly outpacing Moore's law, right? So this is on an exponential scale, right? So this is showing you that there's now a 3.4 month doubling in the amount of computational resources being put into models. So, I think it forces us to ask the question whether or not some of the gains that we're seeing in the performance of machine learning are kind of purely computational, right? So that, there's something that to be said for this, right? Which is that, we're pouring many more resources into using machine learning than we ever have in the past. And so it's important to, kind of reflect on this and ask where is the advantage of machine learning theoretically clear? And there is sort of one region where it is very, very clear that neural networks in particular have an advantage over other methods from numerical analysis. And one of those, the clearest area is in high dimensional regression tasks. So that in part is why potential energy surfaces, like in the last talk, have been such a success story for machine learning in the chemistry community, because it is very, very easy in some sense with neural networks. I mean, in some sense, right? It requires a lot of data typically, but once you have that data, then the problem of actually obtaining a representation of a high dimensional function that is accurate is much more flexible and much easier than is the case with basis functions or grid-based methods. I mean, these things do not scale well with the dimension, whereas neural networks scale extremely well with the dimension. And so that's something that I and many other people have analyzed over the last several years to try to understand precisely what that advantage and trainability and representation looks like. So in that spirit, we're going to try to use neural networks in problems primarily where you have access to data in an online way, so we can regenerate data, and where the task is to represent a high dimensional function. So that's what we want to do. We want to represent a high dimensional function or a high dimensional distribution. And with that, we're going to try to address some of these issues that I was bringing up with coarse graining by having a slightly different paradigm for the process. So the first thing that I'm going to do is build a representation where I project down, just like in traditional coarse graining, but I'm going to allow this projection map to be flexible. So it's going to depend on the state. And the projection itself could, in principle, be nonlinear. And then I'm going to use that projected fine-grained configuration to build a representation of the coarse-grained potential energy surface, which I'll call U hat, right? So this is a function of the coarse-grained coordinates exclusively. And this is something that I can use dynamical simulation or Monte Carlo to sample. I could do importance sampling at this level as well. And then I'm going to take configurations from those coarse-grained dynamics, and I'm going to invert them using a type of invertible neural network called a normalizing flow. Really what I'm doing in this inversion process is I'm sampling a distribution that is conditioned on the coarse-grained coordinate. Okay, so I'm going to take a coarse-grained configuration and I'm going to sample a probability distribution, which is a high-dimensional probability distribution, in which I reconstruct the fine-grained coordinates conditioned on the coarse-grained variables. So in the spirit of, you know, taking high-dimensional functions as a kind of main advantage of machine learning, we're going to learn all of these. So we're going to learn the coarse graining map, we're going to learn the potential energy surface, and we're going to learn this inversion map. Okay, so those are the three things that they're going to learn, and they're going to be learned jointly. So, we'll start with data from MD, in principle, a very small amount. And then we'll start to build this representation, which we will simultaneously learn a potential energy with, and then we'll start to build the inversion, and then we'll feed that inverted data back in at the beginning, right? So this kind of closes the loop, as I was saying before. So in practice, the way that you actually do this looks more complicated than what one might want. So it's it's useful to have these sorts of flexible embeddings, but the exact parameterization of them, is something that's a bit user defined, right? And is not all of these pieces are pretty interchangeable. So I don't want to linger too much on like the specific neural networks or other things that we use, because you could replace this with whichever one you prefer. The way that we do it is based on actually an algorithm from the graph machine learning community, which is called differentiable pooling. So this is really something that's used for pooling and clustering graphs that are very, very large, like social networks. But it's a flexible and useful representation in that it allows you to kind of, in a differentiable way, collect nodes on a graph. And so we use a representation of the internal coordinates. We feed this into an equivariant graph neural network. We've found that equivariance doesn't make much of a difference whether or not you include it. I mean, it's nice to have, right? But it doesn't actually change the results very much. And we build a coarse-grained representation, which now is an abstract one, right? This could be potentially a nonlinear embedding. We've mostly used linear embeddings, so I think the results I'll show you are actually from linear embeddings. But these are now state-dependent projections that will project out the degrees of freedom in different ways at different points in space. So the exact interpretation of the coarse-grained model is now more complicated. We use Schnet to build a representation of the coarse-grained potential. Again, we could replace this with any neural network, and it would be fine. And we do this initial learning in sort of an auto-encoder way, where we do a partial reconstruction of the backbone. So we're simultaneously learning a decoding map, which is a projection that recovers the backbone from the coarse-grained variables. Okay, so those are the main ingredients for the embedding part, right? So this is all really just in parameterizing theta and u. And at the end of the day, we've now kind of given up something, which is that we don't have as clear of an interpretation of our coarse-grained degrees of freedom. So we need to come back and ask, what is it that we actually want theoretically from a model that's built in this way? So the objective that is typically used to train a coarse-grained model, or to parameterize a coarse-grained model, as they would have said at the time that these ideas were developed, is thermodynamic consistency, which is essentially to say that what we desire is that the potential of mean force, or the free energy associated with the coarse-grained variable. So I'm looking at a delta function where I project out everything that maps down to the coarse-grained variable z. I want that that free energy to coincide with the representation of my potential, so that thermodynamic averages that I compute over the coarse-grained system when projected are the same as if I had computed them in the original space and then projected down. So that's that's a notion of convergence that's defined purely in the coarse-grained space. However, with the inversion process, we have the ability to define convergence in the original space, and so that's what we do, which is we use an objective that's inspired by the notion of weak convergence in probability theory, which basically says that two probability distributions converge to one another if expectations computed over some class of observables coincide, some sufficiently large class of observables coincide in the limit of a sequence of measures. So what's useful about this notion of weak thermodynamic convergence, or thermodynamic consistency, is that you could adapt it to specific classes of observables. So the other thermodynamic consistency objective is one that's really kind of universal. It's for every observable out there. This one would allow you in principle to target specific classes of observables. So you could restrict to a class of functions and say, okay, I want averages on some property of my molecular system to coincide with the coarse-grained sampling that I do. And on the left, the coarse-grained sampling here is really saying I sample this coarse-grained model, and then I use the inversion process, which I refer to as a kind of generation probability, and then I compute the average with respect to that distribution. So that's something that will coincide with this if we can reweight. So it's independent of the sampling that I do in p hat, right, in the coarse-grained model. It only depends that this generation probability leads me to the right Boltzmann distribution. Okay, and so we have some theoretical results on this. I won't really go into them. They're just here to sort of say that we understand when weak thermodynamic consistency and thermodynamic consistency are equivalent, and it's basically if you have a big enough set of observables that everything that would be in the thermodynamic consistency framework is holding in the weak thermodynamic consistency. So let me show you what this inversion process actually looks like. So to actually reweight things, what we need to do is actually use an invertible model, because we need to compute a statistical weight of the configuration from the coarse-grained space transported back to the fine-grained space. And that requires that we compute, a Jacobian of the transformation, of the inverse transformation, and, a statistical weight for the inverse map of the fine-grained configuration. Okay, so that to do that, we use a particular class of models that are called normalizing flows. These were originally developed by Esteban Tabak and Eric van den Eijden in 2013, but without any machine learning part. And then they were sort of revisited by Danilo Rezende and others over the last 6 or 7 years. And those models have been pretty useful for learning high dimensional distributions, although there's still many things to understand about them. And so the way that we do this is we actually build a representation of a conditional distribution that's conditioned on the coarse-grained variables. So most of the sampling is actually done by our coarse-grained model. The inversion part is really just doing a sort of reconstruction of the side chains for the most part. And that's a statistical reconstruction. So we can resample this distribution many times conditioned on one coarse-grained representation and build an ensemble of configurations that correspond to that conditioned point. And this is just, so normalizing flows are really flows, right? They're kind of, there's a very tight constraint on the representation here. So they're much less flexible than a generic neural network. I like this representation of a normalizing flow in 1D from a recent paper by Michael Albergo and Eric van den Eyden, which sort of shows you like it really is like a velocity field that needs to be learned. These have to be diffeomorphisms in order to be invertible. And so they were asking these maps to do quite a bit, but under tight constraints. And so the sort of less sampling you can put into them, right? By relying on the coarse-grained sampling, we sort of are able to take advantage of the lack of flexibility in these maps in some sense. Okay, so that sort of tells you that there are a number of sacrifices that we've made, right? Which is that we lose interpretability of the coarse-grained representation, but we obtain more flexible learned embeddings, which are in principle nonlinear. Although I would still emphasize the results I'm going to show you for linear embeddings. And we've also kind of lost mappability of the coarse-grained dynamics. So I brought up already that I think that this is a generically pretty hard problem, but it doesn't stop people from looking at coarse-grained dynamics and imputing meaning onto them. We don't have that option as much, right? The coarse-grained dynamics that we obtain are really kind of abstracted to a level where you couldn't even stare at the coarse-grained model and say, okay, I think what's happening here is, that's all out of the window. But what we obtain are quantitative accuracy on the free energy surfaces and on the Boltzmann distributions, and I'll just show you one result to show you that this is non-trivial. So we can do this for alanine dipeptide, which is the last example, and everything is perfectly accurate, but alanine dipeptide is a pretty easy example. And so we also looked at generating distributions for chignolan, which is a more complicated example, still a small protein, but one that's relatively complex. And what we see is that we can, after reweighting, recover quantitative accuracy on the free energy landscape projected on these two low-dimensional coordinates that happen to be known for the system. In general, this would be hard to do. But we also obtain quantitative accuracy on both large and small-scale observables. So we have the potential energy on the left, and you can see that the regenerated distribution shown in red is quantitatively accurate, and we also capture side chain motions and other things in distribution very, very accurately. Okay, so I'm out of time, so I'm going to stop there and thank the Department of Energy and Google Research for funding this, and then Sriram and David were the two driving forces behind a lot of this work. Thank you.